Hi, everyone. All right, let's continue. So now I'd like to focus a little bit on one property of electrons that we haven't talked about much, but which is very important to the properties of atoms, and that's electron spin, okay? Spin is a kind of intrinsic angular momentum that all electrons, and indeed almost all particles, carry. Here, I'm going to turn to the notebook, 1 second. All right, so it turns out that electrons in atoms can have two types of angular momentum. And these are orbital angular momentum and spin angular momentum. And both of these are important for determining the properties of atoms and particularly for determining atomic magnetism. We've already talked about orbital angular momentum. The orbital angular momentum of an electron is determined by the L quantum number. The magnitude is little l times little l plus 1 square root times h bar. And we found that the z component of the orbital angular momentum was equal to m times h bar. I'm going to call this m sub l, so we know that that m goes with the orbital quantum number, is associated with the orbital quantum number, okay? And recall that L can take on integer values, 0, 1, 2, and so on, up to n minus 1. And that M can take on values such that the absolute value of M is less than or equal to L. And our mental picture of this, well, the only mental picture I have is associated with the Bohr model. I imagine the electron orbiting around the nucleus. Oops. There we are. And of course, carrying, since it's in a mass in orbital motion, it would carry angular momentum. But we know that this picture from the Bohr model is too simplistic, but nevertheless, it gives us some intuition. The other type of angular momentum is, however, is spin. Electrons and nearly all other particles have intrinsic angular momentum. Okay? Which we call spin, which is quantized in much the same way. The magnitude of the spin angular momentum is given by a quantum number S, like so. Don't confuse the capital S, which denotes the magnitude of the angular momentum, with little s, which is the quantum number. And the z component of the spin angular momentum is likewise given by a second quantum number, m sub s, times h bar. Only there's a difference. Here, little s is always equal to 1/2 for electrons. Every electron in the universe has the same value of the spin quantum number s, and it's equal to 1/2. Thus, m sub s, which can take on values from minus s to plus s, spaced by whole number separations, can only take on two values, minus 1/2 or plus 1/2. These are the only two possibilities. Since there are only two possibilities, sometimes these are just referred to as spin up and spin down, okay? So This has some consequences. One consequence is that it simply doubles the degeneracy of all the orbital states, for example, in the hydrogen atom. An electron can occupy any of these states, but in addition, it can occupy it either spin up or spin down. Okay? Now, our mental picture of this might just be the picture of a electron as a little ball that's spinning about its axis. Okay, like so. The spinning ball of charge picture. And that's where the name spin comes from. However, this picture is no more accurate than the picture we drew for orbital angular momentum just a moment ago. It's nice because it gives us some intuition about what's going on. It helps us sort of remember that electrons carry spin angular momentum, but an electron is not a spinning ball of finite size that's spinning about its axis. As far as anyone knows, electrons are point particles with a radius less than 10 to the minus 18 meters, which already is much too small to allow this picture to have any validity. But we can still use it to develop our intuition. Okay, that's electron spin. Okay, here, we can use the idea of angular momentum, both orbital and spin, to explain why some atoms are magnets, okay? So imagine a system where I have an electron that carries angular momentum. So for example, imagine a Bohr electron that's orbiting around in a circle. Now, classically, this would represent a circulating current, and a circulating current would be a magnet, an electromagnet. So a classical model would let us find the magnetic moment of this little magnet if we knew the circulating current and we knew the orbit. So in this case, the magnetic moment would be equal to the area enclosed by the loop, pi r squared, times the current that flows in the loop. And that would be oriented in the direction perpendicular to the loop, which we'll call the z direction. Using just semi-classical ideas, we can see how this changes in the Bohr model. Then pi r squared would be pi times the Bohr radius squared. And the current would be the charge of the electron times the velocity divided by the circumference of the orbit, which would be 2 pi r, or 2 pi a naught. Okay? Finally, we can recognize that the velocity is related to the angular is related to the angular momentum, V can be written as L divided by mr, or m a naught. And that gives us the following: pi a naught squared times E times L over 2 pi a naught squared. And now let's rewrite this one more time. First of all, you can see we can cancel out the factors of pi a naught squared. There we go. And we can remember that angular momentum is quantized in units of h bar. And then we have E h bar over 2m. And so this is what we'd expect for the magnitude of the magnetic moment of an electron in a Bohr atom. And it's just determined by a set of fundamental constants, E, fundamental charge, times h bar, divided by 2 times the mass of the electron. And this quantity has a name. It's called the Bohr magneton. And just as the z component of angular momentum is quantized, this is telling me that magnetic moment in atoms is also quantized, but it's quantized in units of the Bohr magneton. Okay? And where the Bohr magneton we can easily work out as a value of 9.27 times 10 to the minus 24 joules per Tesla. Okay? Okay. That's a small number, but if we make a macroscopic magnet, it'll contain a lot of atoms. Maybe it will add up to something. Okay? Very good. And finally, we should recognize that magnetism can arise from orbital angular momenta. Excuse me. I wanted to say orbital contributions to the magnetic moment. Or we could have spin contributions to the angular momentum. Spin magnetic moment. Which would be plus or minus g times 1/2. Okay, there we are. Just to explain his, we have a factor of plus or minus 1/2 because the z component of the angular momentum associated with spin is plus or minus 1/2 h bar. And then there's a factor of g as well. G is called the electron g factor, pretty imaginative. It comes from solving this problem relativistically because the electron spin has to be treated relativistically. And the simplest theory gives a value for g of g equals 2. So in fact, the contribution from the spin is plus or minus mu v. Okay? Both orbital motion and spin angular momentum can contribute to magnetism in atoms. In fact, both of these can exist, and they're typically coupled together. Okay? In molecules, often the magnetic moment of a molecule will be just determined by the spin angular momentum, because often electrons arrange themselves so that their total orbital angular momentum cancels out. In any event, because of this, atoms in magnetic materials can possess magnetic moments. And in a strong magnet, all of these atoms, all of the magnetic moments of the atoms will line up to produce a strong macroscopic magnetic field. Okay? And I just wanted to, although we're not going to go further with this, I just wanted to show you how this also comes essentially from our quantum treatment of atoms, even from the Bohr model of atoms. Atoms can be microscopic magnets, and in magnetic materials, the magnetic moments of the atoms line up. We have to think about both spin magnetic moment and orbital magnetic moment. Often spin magnetic moment ends up being the dominant surviving factor. Okay? In non-magnetic materials, either the spins don't line up in the solid, that makes something called a paramagnetic material, Or the atoms have a net magnetic moment of 0, which is also quite common. All right, let's stop here.